Okay, today is lecture 6, but actually I will decide not to move to new topics and fill some gaps which are left from in the previous 2 lectures. So we'll still talk about double variable cells and stuff related to them. First, I want to, I made some this remark several times, and probably I will make one more time. Will make similar remarks later, but because I'm really puzzled by this fact, I like this fact that there are 2 different descriptions for double variable cells. One of them in terms of the minors, and as we stated, this is some sort of A variables. They relate the relation with them. If we change the composition or change our network, then these minors are related by some sort of Blücher relation, or sometimes it should be called Q-scalar relation. So this relation of the form xy is equal to ab plus ct. And there is another form of coordinates on the double variable cell, which comes from the decomposition. We represent generic element of the double variable cell as the product of the elementary matrices. I am talking only in type A, but actually all the story exists in any type. So instead of the minors, we will have matrix elements of the on the representations. Instead of the simple matrices, we'll get simple generators corresponding to simple roots. But what is the relation between these 2 descriptions? So let me state the result, maybe here. So we have x coordinates on the double variable cell, and we have also minors, which are A coordinates. And it appears there is a formula, like standard formula, which relate A coordinates to x coordinates. But in order to apply it, we need first to do some special map, which I denote here by zeta, and this map is called twist map. This map was invented by Fomin Zelevinsky 25 years ago, like this, for double variable cells, and then it is found in many examples of cluster varieties. And I can repeat it. I want to understand this story better, but anyway, let me give you an example. And example which I'm going to give, which will correspond to GL3. And I take the follow, and as a cell, I take the open cell inside the GL3. So it will be cell which corresponds to W0, W0. I take reduced decomposition of W0. So first, such things which correspond to S bar. I don't know who cares, but before I used to write pictures where with slanted edges. But now I move to vertical edges and decide this is better for some reasons, or some conventions. Anyway, just in case somebody noticed. So we have here we have first S2, S1, S2 with bars, and then S2, S1, S2. And the corresponding group element has the following factorization: F2, F1, F2, then E2, E1, E2. And after each E or F, we have H with the same index. And we have 9 variables, which correspond to the faces of the corresponding graph, or connect components to the complement of this graph, if you want. Okay, now the most non-trivial formula in this example is this G prime. So we take matrix G and then construct another matrix G prime, which consists of some, you see, there's some minors of G which are used this way. I will not explain origin of this formula, but I rather state the consequence of the existence of this formula. And the consequences are like this. So here I repeat my picture of the network. On the right side, I label the faces via zigzags. Maybe you remember we had the rule that we have orange zigzags which go this direction and green zigzags which go in this direction. And to each face, we can look to the numbers of orange zigzags which go below it and green zigzags which go below it. And here I put the corresponding numbers. There is a small issue that here my number differs from the one which I used before. So actually here I label zigzag by the ends, but it is not. So practically on this picture, it means that orange zigzags are on the beginning are labeled from the bottom to the head. Maybe I can even stress it somehow in the picture. So when zigzags ends, they are labeled from the bottom to the top, and where it's green zigzags, and they again labeled from the bottom to the top. And now we can apply some standard map, which we had from the A variety, A coordinates, to X coordinates. And it appears that the result that what we have X coordinates here and A coordinates here agrees if we substitute to this map not matrix G, but the matrix G prime. For example, we can compute what is the coordinate corresponding to this face. According to our formula, this how the map looks like. X is equal to product of A xj, xi in power bij. So we should multiply the. We will have the fraction, and in numerator we will have A coordinates such that the corresponding H goes to J, and in the denominator we'll have A coordinates such as corresponding H goes from J. So for this face, in numerator we will have this and this, I believe. And in denominator, we will have this and this. And here is the formula. So you can take this element, multiply by the term, and divide over this and this, and get it. And actually, this formula works for all internal faces. One can ask what happens for the others, for the faces, other faces, and answer the formula like this with small correction. I'm not going to write down this explicitly, but in words, it will be still monomial transformation. We'll have products of the A variable, and this product will equal to sum of to this x variables. But for A variable which correspond to the boundary, we will have to somehow change the powers. Powers still be integer, no this half integers which we had before, and we'll have in 15 minutes for the Poisson bracket, everything integer, but should be some care for the boundary. So this is a twist map. So in some sense, this is a map which relates to cluster structures of the same manifold. Okay, maybe one more remark. Okay, I have a couple of the same pages. Maybe this is not this page not necessary. This is also. And here, one can ask what happens if we use the same formula, but not for M prime, but for original matrix. Why do we need this strange twist transformation? Okay, so in terms of formula, it means that here we consider minors which correspond to original matrix G. And let me state what will be the result. I have to look to my okay, so here will be x4 and x7 remains, but instead of x5 we will get one plus x4 inverse 1 plus x7 inverse of x5. Instead of x6, we will get 1 over so this is a computation for original matrix. So you see that these are not monomials, these are not original x variables, but actually these variables are related to original x4, x5, x4, x5, x6, x7. By first of all, but you see we have denominators, so 1 plus x4 and 1 plus x7. So actually this is a mutation in x4 and x7 plus inversion. So if you mutate in these two in such x variables, then these two variables will be inverted, and x6 will be multiplied by this, and x5 will be multiplied by 1 over this. And so after all inversion, you get. So at least in this example, this twist map is some sort of mutation. There's no trivial map from one matrix to another. It is some sort of mutation. This is a relation between two structures. Okay, this is what I wanted to say, at least now, for about twist map. Questions? Probably no. Okay, now let me return to the topic which we discussed last time. After some talk about positivity, we started to discuss about Poisson structures. So first we defined cluster Poisson structure. So if you have X cluster variety with variables X, then we can define a bracket by the formula that bracket of xi and xj is equal to bij xi. This is logarithmically constant. So in this formula, this bracket is quadratic, but if you consider logarithmic coordinates, then the bracket will be constant. And the theorem which we stated last time, and today I'll comment further, that this is a bracket is equal to standard, which is so-called Sklenin bracket on the Lie group. I restrict myself to the type A. So let's take the classical R matrix by this formula. Coefficient 1/2 is, I think I checked. It's correct. I mean, the bracket can be any by any formula, but in order to exactly coincide with the cluster bracket which I introduced, we need this, I believe we need this coefficient. And the bracket is defined by this formula. Such maybe strange notation, comma and tensor product means that we consider the matrix of the square of the time of the size n squared times n squared. So we consider tensor product of these two matrices, but instead of multiplication, if we take tensor product of two matrices, the matrix elements of the result are products of the matrix element of the first and second factor. And here we, instead of the product, take the bracket. So, okay, in terms of the coordinates, this formula is equivalent to this formula. That Poisson bracket of G of two given matrix elements of G is a matrix element of the right side of the commutator. Okay, so the property that this is a Poisson structure. This, moreover, this gives a Poisson-Lie group structure, and double RSL are Poisson's manifolds. Let me comment on Poisson-Lie property. So, theoretically speaking, okay, let me comment Poisson-Lie property. What does it mean? It means the following. So, if we take, so as stated, it is a following property that we have a multiplication map from G times G to G, and the image of M star of P plus P is equal to P. P is a Poisson P vector, the element of the second power of the tangent bundle. In particular, this property means that such image exists. So if you have, I mean, this map is not embedding. So if you have two different points, if you in G times G which goes to the same G, then this images of the pi plus pi coincide. Another way to think about it, actually prove it, is the following. So let us assume that we have some element G which is factorized to G1 times G2. So any matrix element of G is some bilinear combination of the matrix elements of G1 and G2. Hence, we have two ways to compute bracket between matrix element of G. One is just use Sklenin bracket, I mean, apply this formula. So bracket of two matrix elements of G will be given by this, also known as actually quadratic formula. Okay, but there is another way. we can consider this element as a product of matrix element of G1 and G2. And then say, okay, so for G1 we have poisson bracket. For G2 we have matrix element of G2, we have poisson brackets. So we can compute either on G1, either on G2. And G1 and G2 commutes. And this is what actually this m star of pi plus pi means. Poisson property states that these two ways to compute bracket actually coincide. And this follows from the computation with commutant. So we compute this bracket, by definition this is this. Now if we substitute G as a product G1 times G2, then the commutator has the following decomposition. And in first term we just compute bracket of G1 and multiply in G2 times G2, and second is vice versa. So we get that pi is equal to m star of pi. So Poisson property is actually obvious. What is essential, what is really non-trivial is a Jacobi identity. It's the fact that we actually define Poisson bracket. And this follows from Young-Baxter equation. There's some computation which I omit and decide not to give as a problem. Or decide to give as a problem, it is to compute everything for the case of GL2. Okay. And now the theorem for Goncharov that if we restrict this bracket to the double Bria cell, then this bracket becomes cluster Poisson bracket. They stated, and so the theorem is not for GLN, but to be more precise, for PGLN. This is not, okay, maybe not big difference, but on the practical computation, I'll do computation for SLN. It will mean that, I mean, probably you will not notice it in the computation which I actually put on the slide, but computations were behind done for SLN. In practical, it means that before we for Cartan element HI, we assign the following matrix X, which has I x's and then all ones. This matrix does not belong to SLN. And in order to consider corresponding matrix as SLN, we should divide it by its determinant in the power 1 over n. So we get this matrix. So here is minus I over n. I don't know whether it's visible, probably not. So this determinant matrix has determinant 1 and up to constant torus is equivalent to this matrix H which we had before. I'm doing computation for SLN, but this function which I consider, they're not good in terms of coordinates because they involve some roots of x's. But if you consider functions which do not depend on the roots, then they apparently become functions on PGLN. So I'm doing computation on the not PGLN but on its scalar SLN and use the functions which are actually defined up to the Galois group, up to some roots of unity. But whether you restrict everything to the functions which are invariant on this Galois group, then this function actually functions of PGLN, and hence we proved formal statement for the bracket of PGLN. Okay. In particular, now these H's rather correspond to simple roots. we don't, and for 7 we have only n-1 simple roots. So n's matrix now become equal to 1, which is clear from this formula. So we will not use it in our factorization. Idea of the proof of this theorem is the following. So we have to prove it for any double Beer cell. We proved it for simplest double Beer cell, namely cells, which correspond to simple reflection here or here. Maybe even before we should prove it for case where U and V are identity. So this theorem, maybe I should write it. P restricted to C on the torus is equal to 0. This is, for example, this can be seen from this formula that we take our matrix and then either then you move it to the point G using either left shift or right shift. But our matrix is invariant on the joint action of the Cartan. So these two terms are equals and pi is equal to 0. So on the Cartan, pi is equal to 0. So the next simplest cases are the cases where U or V are simple reflections. And here is the result for the case where a simple reflection is the first one. Then the corresponding parameterization has includes one F, so many H's, then one F. Number of variables is n. Let me recall that here there is no H and n because there's no identity. And the statement is that now the Klein bracket on this cell is equivalent to the following cluster bracket. So bracket between this xn and xi variable which correspond to i's Cartan element here is equal to xi xn. Maybe xn xi will be more suggestive, but that's not important. And variables, and also there are some non-zero brackets with the neighbor x's, xi minus 1 and xi plus 1. Maybe it will be more clear if I show this from the picture. So this is a picture for GL4, or maybe better at PGL4. We have variables x1, x2, x3, and one S bar. So one vertical edge with a black end on the top. So which corresponding variable x4. Then, according to our rule, we'll have arrow from x4 to x2, and this arrow corresponds to coefficient 1 here. And also we have such two oriented triangles, but these two triangles are dashed. It means that the corresponding elements of the matrix BIG are halves. One can think that here also in something half, but this we have two halved triangles, but on this edge, these halves added to the one. For example, one of the properties of this corresponding matrix that for each edge, number of ingoing edges equals to the number of outgoing edges. But of course, you should compute all this with multiplicity. For example, for this edge, you have one outgoing edge and two halves of the ingoing edges. as a result, you have 1 equal to 1. And similar for any other h. Of course, all 4 variables which are used here should be viewed as a frozen, because we have not integers values of the h. Sorry. Okay. I added the same page because now I want to state similar result for another maybe this will be a problem like lemma. It's too much. Put everything as a problem for another cell ESI. In the factorization formula, what changed? We'll have here E instead of F. In terms of the bicolored graph, we will have black. We will have black and vertex below. So it means that our H is now directed in this way. Recall that the rule is that near the black edges, of the near the black vertices of the bipartite graph, edges goes clockwise, like this. So now this is black, so H, and half edges also should go clockwise, now like this. And around white, they goes counterclockwise. So like this. In terms of the formula here, it will mean that we have to change all signs. But here's the okay. And now I'm going to state that this is actually sufficient. So using these two construction, one for simple reflection S, another for simple reflection S bar, we can construct a cluster Poisson bracket and prove the theorem for any double Brière cell. For this, we will need a procedure which is called by Fogg-Goncharov as amalgamation. Let's forget for just a quick second all the previous story about algebra cell, and now I state the I'll give you the general definition. So suppose we have one seed. So now I'll write seed in a bit different manner, more formal. So seed will consist of the following. So we have set I. We have set I F, And we also have some so I is a set of vertices, and IF is a set of frozen vertices. And maybe let me also write down X for the set of variables. Xi. Assume that we have one more seed, 2. Now the set of vertices will be J, the set of frozen vertices will be GF, incidence matrix will be BJ, and we have some variables XG. And assume that we have some subset L some set such that which has 2 embeddings, one embedding to IF, another embedding to GF. Assume then we can define amalgamation. Definition. Of the all seeds above is the following set. So we have K is a seed K, KF, where the K is U union G by L. So I take disjoint union of the set of vertices I and J, but I glue them via L. So if for any element of L which correspond to two vertices, one frozen in first seed, another frozen second seed. So I glue the corresponding vertices. Of course, similar I do with the frozen part. And for incidence matrix, I can write down the formula, of course. So BKIJ is equal to, but the most important formula is the following. So it will be Bij I plus Bij J if both vertices I and J belongs to L. Other cases which I meet, for example, if it is 0, so if I belongs to I minus L, and J belongs to J. Or verse, or opposite. Or it can be, it is equal to Bij I if I belongs to I minus L, or and J belongs to L. Or opposite. And there is also a case where it's BJJ. And the last thing to define are the variables. So x ki is equal to xi I if I belongs to set of vertices. Or maybe I put it here. Okay, set of vertices I without L, xij if I belongs to j minus L, and finally if I belongs to L, in other words, belongs to both set of vertices of the first seed and second seed, it is just the product. This is the definition. Are there any questions about this definition? Okay, can somebody confirm that you can still hear me?
Yes, we do.
Okay. Okay. As I said, pictorial, it means that we take two quivers and then glue some vertices, those quivers. And the corresponding, and if two vertices are glued, then the number of edges will equal just the sum of the number of edges of the first and the second graph, the first and the second quiver. Of course, we should use have in mind the orientation. Okay, this is the definition of the amalgamation. Then let me give a remark which will be used if for some I from L all Bij becomes integer, then we can unfroze variable xi. And this is what we will actually do. We will take our simple seeds which correspond to simple reflects and then glue them using amalgamation and unfroze variables if we can. The key properties of this map are for the stuff are the following. Okay, let me put it as a lemma. Okay. Amalgamation is Poisson map. The only point where one have to check something, the only, of course, this is somewhere near L, near glued part. So, and this multiplication of corresponding variables, by the way, here should be J, exactly agrees with the summation of the in the matrix B. Maybe property B, which is also obvious, but amalgamation commutes with mutation. So if we, of course, we can mutate here, we can mutate only on unfrozen variables. But, so if we mutate on some unfrozen variable and then glue, it is the same that if we mutate in the image of this unfrozen variable here, if it is the same as we first glue and then mutate on the image of this unfrozen variable here. So amalgamation is a cluster. Before I state the main theorem, let me first consider an example. This example will correspond to so-called Coxeter elements in the while group. So C is a Coxeter element. If it is a product of all simple reflections okay, let me write it as a formula. It's a product Si1 Si(n-1), where the set of indices I1 In-1 is a permutation of 1 and -1. So in other words, this is a product of all simple reflection. Each of them are taken on the ones. Is taken on ones. This is another quite special element, or better to say set of elements in the while group. So usually people talk about reflections, simple reflections. After some work, people realize that it's very important to look at the longest element, and Coxeter elements also play a special role. For example, it can be proven. Okay, you can state it as a theorem. All Coxeter elements are conjugate. Of course, in terms of the simple of the type A, this obvious theorem, all the Coxeter elements are just long cycles of Rankine. But it's true for any root system. And order of this element C is H Coxeter number for example, one can show the following formula for H. H is I think this. Okay, at least. Okay. In principle, it's not even completely obvious that y is an integer number. Y is a dimension of the g, which is more or less. Instead of dimension of g, one can write number of roots in root system. One can divide the number of roots over the number of the dimension of the space in which root system lives, but it is integer. Okay, so this Coxeter element, these are the Coxeter elements, but I'm going to talk about the corresponding Brios cells. So let us take, so actually examples probably starts here. So we can take the Coxeter, the Brios cell, which correspond to the following S1, which will correspond to two Coxeter elements. Let's take for both of them such decomposition, S1 and S2. Then what we'll have in terms of network. Okay, I draw 5 lines. So actually, so this picture for SL5. But just, of course, for concreteness. Of course, I took this element. I have to also specify what kind of reduced decomposition I take. For Coxeter element itself, there is no way to change reduced decomposition because there is no way to apply any braid rule. We have only one generator of each type, so there's no room for. Okay, not literally correct. We can just, if two reflections, two indices differs greater than one, of course we can permute them. Maybe I'll talk about this in a moment. But let me, for concreteness and in order to have agreement with example which I considered while I prepared my talk, my lecture today, let's take this reduced decomposition. So first we have bars, and then we have just simple reflections. Okay. In this case, we first draw such horizontal edges, and then again such horizontal. For barred as black vertices on the top, and for not barred on the bottom. In principle, here are the white vertices. Okay, in particular, you see that in order to have honest bipartite graph, I should add black vertices here. And how then the graph will look like? around the black vertices we go clockwise. So we have edges here. And here we have some sort of half edges. What kind of edge we will get between these two faces? Or maybe even before, no, before I should draw this. Between these two faces will have no edges. It is clear from the picture of the bipartite graph. We can draw these two edges, but they cancel. Or it is clear from our gluing procedure. How to say it? So first we get this edge. So we draw such triangle. And then we had this edge. So we draw no, maybe not. We have this edge. And then we have this edge, which is such triangle. And after amalgamation, these two half edges disappeared. They cancel each other. So we have no edges between these two vertices. Okay, what are the lessons which we can learn from this example? First of all, we actually have unfrozen variables. Unfrozen variables, as usual, will correspond to the bounded faces. For these faces, we don't have half edges because for any I mean, we don't have half edges between two unfrozen variables, between two bounded regions. Because for each such case, if we had some, they either become of the same direction, so they come here, or the opposite direction. And they goes to nothing. So if we have two half edges, then two closed faces, and at one point one of them opens, you get half edge, and then another of them closes, and we get another half edge, and everything is constant. So here so in this example, we have n minus 1, the picture 4 unfrozen variables, but actually no edges between them. Let me take another example, again, of the Coxeter type, but of the different. So I take S1, Sn minus 1, and here I take another Coxeter element, Sn minus 1, S1. Again, PGL5 picture, or maybe, okay, actually, I believe PGL4 will be sufficient. And now what will be the picture for the graph? As before, horizontal edges are clear, because here we don't have actually half edges, it's just like this. Now what will be the edges between these two? And here you see we have now we have this and this, because this edge goes clockwise around the black vertex. This is yeah. So again, we have these two faces closed. First, we open one of them by this edge, and we get this and such half edges. Then we close it and get half edge this and half edge up. And these two half edges, they add to each other, and we get honest edge in this direction. So you see, we took different Coxeter double cells, and in one case we have just empty quiver for an unfrozen part, and here for unfrozen part we get type A quiver, just linear quiver. And then to the lecture, I plan to say that in some sense, for some problems, all Coxeter cells are equivalent, but not for this one. Okay, now I want to somehow finish the story about Poisson structure CUV. So if I take any double Fourier cell, then I glue so how to say, take amalgamation so I fix the reduced expression, like reduced decomposition, take an amalgamation of C S E I and unfroze variables or beta vertices corresponding to closed faces. And in this way, we obtain a quiver and bracket, and due to Poisson-Lie property, and lemma's facts which I mentioned above, this problem is lemma that on the cell which correspond to simple reflection, this cluster bracket coincides with Kleinen's bracket. And lemma 4. We get we get that cluster bracket equal to square. Okay, and this end of the proof. Questions? Okay, I have like 15 minutes. Let me check. Or maybe even 20. And I want to spend this time in the application of this construction in the theory of integrable systems. So let us now consider below we consider double Fourier cells. Now let us consider these double Fourier cells which are quotient by adjoint action of the cartan. What does it mean practically? So it let's take example. So let's take double Fourier cell as which is a Coxeter one, x1, x2 in PGL3. When you take quotient by the action of the cartan, it is now this p is even less important. But anyway, a generic element here is represented like this. So first we take the product of cartan generators. Then we take reflection, cartan generator, reflection, cartan generator, reflection, cartan generator. Maybe I even prefer to permute these two because it is also possible. Here F2 x5 E2 x6. If we take the quotient of the adjoint action, we can remove this H1 from here and move it here. And the same we can do with H2. And here should be H2 of x6, and here is H1. And you see this H2 can go and hit on this X. So under the adjoint action, equivalent by the adjoint action of the cartan to the following product. We can remove this cartan generators which we had at the beginning and move and put them here. So here instead of x6, we get x6, x2 x6, and here instead of x5, we get x1, x5. Because h commutes with all h's and both ins e and f other than its own. So h are some sort of weight generators. And weight generators do not compute with root generators only for its root. So you see, so after this quotient, so here we have in some card we have 6 coordinates. After the quotient we have 4 coordinates, and the coordinates are naturally glued. So it means that this quotient has a natural cluster structure, which is obtained by gluing of vertices which we have on the left and the right, on the left and the right of our diagram. So here, what I wrote F1, E1, F2, E2. And vertices are, and edge variables are here, x1, x2, x3, x4, x5. I see. Sorry. Here is h2 of x5. But this h1 which we had, it goes successfully here and appears here. So this h1 goes here and through h2, e2, h2, f2, and finally gets here. And in this quiver, we can glue this and this, and this and this. And in this case, we have no more frozen variables. And we get honest cluster structure. So, okay, here is the example. And the claim which we have, we glue or amalgamate if you so we have 2 steps. First, we glue vertices on each border, and then we unfroze them. And this, for example, in this case, what do we get after such procedure? We have such edges. And here we had half edges, but after the gluing, these half edges cancel each other. So here we had half edges in this direction. Here we had half edge in this direction. After the gluing, they cancel just. So in this example, after the gluing, we get the following quiver. So our vertices will be x3, x1, x4, x2, x6, and x5. Yes, maybe like this. And here we have one arrow. Here we have one arrow. What is how many arrows we get from x3 to x1, x4? We had one arrow here and one arrow here. So after the gluing, we will actually have two arrows in opposite direction. Here we also have two arrows. And no more frozen variables, everything is done. Okay, so this is the quotient of the double grass cells. And you can ask, where is the integrable system? And if I want to consider, look to the quotient, I have to consider functions which are well defined on the quotient. So which are well defined on the which are well defined under the conjugation. The natural functions of this form are traces. And indeed, there is the following lemma. Let us define hk is 1 over k trace g in power k. Then the Poisson bracket between hk and hl is equal to 0. And maybe for the speed, I will just copy a computation from some which is written here. Sorry, here. So we can put a bracket between trace g in power k, trace g in power l. It is the same as a compute just all bracket between all matrix elements, and then takes the trace of the result. Trace with respect to tensor product of vector space. Now, if we compute bracket between these two things, then we should pick one of the factors here, one of the factors here, compute their bracket, and so we get this formula. Now note that this bracket is given by R matrix. At this point, I use R matrix structure. And it is easy to see that this is maybe up to some factors which I lost somewhere, is a commutator of R and g in power k and g in power l. And trace of the commutator is equal to 0. So we are done. Now let's do some counting. first of all, if we take standard double Brillouin cell CUV, what is its dimension? We take reduced decomposition, which has a length of sum of the lengths. And also before, in the beginning, we should put general cartan, for example. So it will be, if it considers this double Brillouin cell in SLN, then the dimension of the corresponding manifold will be like this. Now, if we take the corresponding double Brillouin cell, takes its quotient with respect to the adjoint action of the torus, then we glue frozen variables on the right border and the left border. And we have only one frozen variable for each row. So the dimension of this will be just L of U plus L of V. If UV contains simple reflection which correspond to any root, Si or Si bar for any I. So now if we take Cox tetra cell, some cell which C prime, where C prime are Cox tetra elements. We have dimension of this Cox tetra cell is equal to 2 times n minus 1, because C prime contains one, each reflection contains only once, so 2 times n minus 1. And we have n minus 1 commuting Hamiltonians, HK. We can trace G in power k, but since our matrix belongs to a cell, so this is a symmetric function of the eigenvalues of matrix G, and since my matrix belongs to a cell, so the all exactly n minus 1 algebraically independent eigenvalues here. So number of commuting Hamiltonians is a half of the dimension of the space. So we get integrable system. And this integrable system is called TODA. To be more precise, what is usually called TODA, it is an integrable system which we obtain in such manner for choice, for this choice of the Cox tetra element. And for another choices of Cox tetra elements, we obtain integral system which looks a bit differently, but actually they're equivalent due to mutations and so on. Maybe the last remark. that quivers corresponding to one reduced decomposition SI1, SI in capital, and another reduced composition which differs by moving SI1 by conjugation or by SI1. So SI2, SIN, and then SI1. So such quiver coincide. Because if you take, because we do, I mean, now we draw this vertical edges, but since we glue the borders, one can think that they draw them on a cylinder. So all these lines, actually not lines, are circles. So it doesn't matter. So this line can somehow go and appear in this point. It means that we have actually more. So hence different double barrel cells lead to equivalent cluster varieties after quotient by adjoint action. Okay, I'm out of time. So questions. I don't know why this big square appeared in my would know, but I try to make it invisible. Okay, if there's no questions, I stop.